In this video, I'm going to discuss the steps involved in designing and conducting an experiment. So first of all, we need to talk about the terms independent variable and dependent variable. An independent variable is a variable that's manipulated. So for example, if you were doing a drug trial, the dosage of the drug would be the independent variable. It's the one that's being manipulated. Now the independent variable is typically plotted on the x-axis of a graph. If we look at the graph that I've made here, we have drug dosage. I didn't put the units in here, but we have three different dosages, 0, 10, and 20. And then, okay, if that's the independent variable, what's the dependent variable? Well, the dependent variable is the variable that depends on the independent variable. So depending on what the level of the drug dosage is, we may have different effects. So in this particular case, I have blood pressure as the dependent variable, and that's typically plotted on the y-axis of a graph. And you can see here I have a line drawn in red, and you can see at a drug dosage of 0, you have a certain blood pressure. At a drug dosage of 10, you have a slightly lower blood pressure. And at a drug dosage of 20, the blood pressure is even lower. So we can see there's a relationship here, okay? And we'll talk more about that sort of relationship in a moment. But again, we have an independent variable, that's the variable that's manipulated in an experiment, and the dependent variable is essentially the outcome. It's the result. So in this case, we'd be measuring blood pressure in our patients. Another term we need to understand is the term controlled experiment. You may have heard this term in the news. A controlled experiment is an experiment that's been designed very well, may take months of planning to design it. They would ask people to then join into, say, a drug trial or something like that. And basically everything's controlled as well as possible. So all these different variables are controlled, such as the age of the subjects, the health of the subjects. Everything you can possibly think of is controlled as best as one can. And the idea being that there's going to be one variable which we're going to manipulate, again, which would be something like drug dosage. So we really just want that one thing changing or being manipulated, and everything else is controlled for. So that's the meaning of a controlled experiment. Now, there have to be at least two groups in an experiment like this. You would have an experimental group and then a control group. Now, it's actually possible you might actually have more than two groups. You might have a control group and then perhaps two experimental groups. And that's actually shown here in this graph. We have the control group that's given a dosage of 0 for the drug, and then two experimental groups, one that's given a dosage of 10 and another that's given a dosage of 20. To keep things simple, I'm just going to discuss things as if there's just two groups, an experimental group and a control group. Now, each group will receive the same treatment except for that one factor being tested. Again, it's a controlled experiment, so the only thing we're going to vary is the drug dosage. So again, an independent variable is the one that's being manipulated, and the dependent variable is the one that's measured. Let's move on. So, okay, now let's imagine that we are going to do a drug trial. So we have drug X, and we think that it may reduce blood pressure. So our hypothesis is that drug X reduces blood pressure in patients with high blood pressure. Now that's fairly broad, right? That's a hypothesis is a fairly broad positive statement such as that. But it has to be testable with things we've discussed previously. Now, based on that hypothesis, we then make up our prediction. The prediction is much more specific. So in this case, we're going to say a 10 milligram per day dosage of this drug X will reduce blood pressure in adult male and female patients with blood pressure in the range of 140, which is the systolic pressure, that's the higher pressure, over 90. 90 is the diastolic pressure, that's the lower blood pressure. So you may recall that a normal blood pressure is about 120 over 80. So someone with 140 over 90 millimeters of mercury would actually have elevated blood pressure. So in other words, they have high blood pressure. But we're going to limit it to patients with that as the minimum blood pressure. And then the higher range would be 159 over 99 millimeters of mercury. So we're sort of excluding the people with extremely high blood pressure. So these people clearly have high blood pressure. It needs to be treated, but they're not at the extreme end of extremely high blood pressure. So that's going to be our group. So we now select a large group of people. over a certain age range. Let's say we're going to use adults here. We'll have male and female participants in the study, and they're going to be randomly assigned to two groups. So that's very important that we randomly assign them. So they'll have roughly equal numbers of males and females in both groups. We won't just have older people in one group and younger people in the other group, right? They're all, in terms of ages, they'll all be mixed up in the two groups. Now, okay, we've done that. We've divided our group randomly into our subjects into two groups. One group will receive the medicine over a certain period of time. Let's say 2 months. Okay, we're going to do a trial of 2 months. Now, the other group is going to receive what's called the placebo. A placebo is a pill that doesn't do anything. So it's typically just a sugar pill or something like that. So it has no effect. It's not going to hurt them. It's not going to harm them. But the main point is they'll be receiving a pill. They'll be taking a pill every day. And they may think that, it's actually medicine, even though it isn't. Now, why is it important to have a placebo? Well, there's actually something called the placebo effect, in which when you give medicine, even if it's not a real medicine, but just fake medicine in the sense it's a placebo, like a sugar pill, the patient may actually show some improvements. And the reason for this is that psychologically they feel like, oh, I'm being treated now. Maybe I'll feel better. Maybe this will have an effect. And you can imagine that if you have high blood pressure, the more relaxed you are, the lower your blood pressure. So we want to sort of control for that effect, this potential placebo effect. So the control group, they'll be receiving this, essentially a fake pill that has no medicine in it. Now, we're going to also do a double-blind experiment. So not all experiments are double-blind, but the very best ones are. This is where an experiment which the person giving the drugs doesn't know which group the person belongs in. So they don't know if they're, like, imagine that instead of a pill, maybe you have to go in and get a shot daily from a doctor or a nurse. Well, the doctor or the nurse wouldn't actually know if they're giving you medicine or not. Now, this seems kind of, deceptive and bad, but actually there's a good reason for this. If the doctor or nurse knows that they're giving medicine, or if they know that they're giving placebo, it may affect their behavior or what they say, even subtly, if they're, and so it's best that they don't know. Now, obviously, someone's going to be keeping track of what's the real medicine and what's not. And then, so those people, the people that actually do the data analysis would in fact know. But it's called double blind because the patient doesn't know, and the doctor or nurse that's actually giving the medicine that's in direct contact with the patient doesn't know either. So there can't be any sort of psychological bias. Okay, so finally, let's move on. So we've set up our study. Now what we do is we measure blood pressure. Let's say we do it every day. And then we're going to compare our results with the predictions. And there's really a couple possibilities of what can happen here. The hypothesis can either receive support or it can be falsified. Now, I've actually drawn both possibilities in here. So if you look at the graph that I've made, the red line represents a situation in which the hypothesis receives support. I've actually have two doses instead of just one, just to make it a little bit nicer of a curve to look at. But we have a dosage of 0, 10, and then 20. And what we're saying is after 2 months of drug X, people that were given a dosage of 10 of drug X, well, they have a lower blood pressure than the people that have received the placebo or a dosage of 0. And the people that were given 20, a dosage of 20 of the drug, well, they have even lower blood pressure. So this certainly supports the hypothesis that drug X reduces blood pressure in the case of hypertension or high blood pressure. Now, there's another possibility, which I've illustrated with the purple line, which is just a flat line. So basically it's saying, if you look at this data, it didn't matter whether a person received the placebo, a dosage of 10, or a dosage of 20. In all three cases, there was no difference. In other words, the drug didn't really affect, it didn't make them anything worse. It didn't give them hypertension, but it certainly didn't lower their hypertension or high blood pressure. So it appears that in that case, the hypothesis was wrong. And when a hypothesis is wrong, we say that it's falsified. So in science and medicine, you can falsify a hypothesis. You can prove it wrong. On the other hand, the case with the red line shows that, okay, there was a reduction in blood pressure, And you would say that, okay, the data support the hypothesis. We never say, again, I mentioned this in a previous video, we never say that we have proved the hypothesis. We just indicate that the data support the hypothesis. And then we would do more tests and so forth to further shore up our data and our understanding of how this drug works and so forth. There may also be more experiments needed to determine safety and efficacy of the drug. So we give it to certain patients, but maybe we have to be very careful about giving it to patients that are extremely old or have extremely high blood pressure. So new drug trials would have to be done with those groups to see how safe the drug is. Finally, there is a last step, which is if the scientists and doctors do all this work and they don't tell anyone about it, it doesn't do any good. So they have to make their findings known. So findings are disseminated in peer-reviewed journals. A peer-reviewed journal is a journal in which the articles are essentially looked over in extreme detail by experts in the field. They'll make suggestions on how the article can be improved in terms of clarity of the presentation. They actually may suggest new experiments that need to be done. They may even reject the paper and say that there's some methodological problems or something like that. But eventually, if everything was done correctly, then the paper would, after some modification, be ready for publication, be then disseminated through the journal. Results, again, so when we do an experiment like this, the results are only assumed to be valid for the conditions in which the experiment were done. So in this particular experiment, we looked at patients perhaps of a certain age range, and I mentioned the blood pressure range for these patients. Well, we don't know, for example, that it's definitely going to work with patients with, say, even higher blood pressure. So a whole nother study would have to tackle that issue. Okay, so basically that brings us to the end of this. So I've talked to you about how a controlled experiment was done. I've talked about the idea of a placebo, how that's important, how we have an independent variable, which is the one that's manipulated, and a dependent variable. And we've also discussed the idea of, a hypothesis either being supported by data or a hypothesis being falsified. So I'll stop there. And thank you for viewing this video.